Welcome to another video. Our previous video went through some of the generalizations that would be involved in moving from a scalar learning framework to a multidimensional or vector learning framework. And we saw how linear algebra can be useful in maintaining those compact Bayesian updating formulas. And in this video, I wanted to demonstrate how we can actually estimate the parameters of a learning model in a very, very simple setting that is laughably unrealistic, but we have to start somewhere, and this is a great place to start. We're going to estimate a simple learning model, and we're going to assume that there is no censoring and no truncation. We're going to use log wage residuals as the signals, and the thing that is being learned about is the individual's own ability in the labor market. The estimating equation is going to be a very simple log wage equation adapted to the panel data setting. We've got the log of the wage as a function of covariates x and its linear in parameters. And then we have the familiar composite error term, a sub I plus epsilon sub it. And one thing I should emphasize here is that there's no selection into the labor force. We're just taking everything as given. You could think of this as randomly assigned jobs. We're making this as simple as possible econometrically so that we can point out how to empirically apply these learning models. So what do we hope to get out of this estimation? Well, we hope to, by placing distributional assumptions on a sub I and epsilon sub it, to estimate the parameters of the learning model by maximum likelihood. And the key parameters we're trying to estimate are the slope coefficients and the two variance components. And we can estimate these by maximum likelihood. And then once we have these parameters and the sequence of signals for each individual, which is just given in the data once we have the parameters, then we can compute each person's beliefs at each point in time under this Bayesian updating framework. And then, because this is a linear panel regression, we can compare our results with other panel estimators and see if there's anything different. And one thing in this particular case is that we're assuming that the a sub I is independent of the x's. And in this situation, we can use the random effects estimator to estimate our learning model parameters. And the key reason we can do that is because there's no selection into getting the signal. So let's jump into some Julia code now and see how this is done. We've got a Julia script here, and the key libraries that we're going to load in are fixed effect models and mixed models. This is how we do linear, fixed effects, and random effects in Julia. These other libraries are just basic data manipulation and statistics and random numbers libraries. And you can follow along with this code. I've posted it to the companion GitHub repository, and there's a link in the video description if you want to follow along more closely. Basically, there's some data that I've got that I've posted alongside this. It's very simple data about the labor market, and we're going to throw away, for estimation purposes, we're going to ignore any missing wages, which would be coincident with non-employment. And we'll run a fixed effects estimation. We'll then run a random effects estimation. And then given the estimates of the random effects model, that's going to coincide with our learning model, as I just said. And then from there, we can take those parameters and actually compute the signals and the belief updating for each person in the sample. So I don't know that there's something to be gained from going through the code line by line. I just wanted to kind of give you an overview of how the code is structured. The signals are just going to be the wage residuals that are going to be the composite error term that's going to include both A and epsilon. And then the belief updating is just more a trick with the programming to make sure rows of data are lined up appropriately. And you can notice in this section that there's the familiar formulas that we just went over in prior videos. So let's go through and run this. So again, I've got Julia installed in my VS Code, so I can just push play and it will execute everything. So let's go ahead and run the code now. All right, the code's finished, and I'll bring the results up in full screen so that we can look through them. Our first model, the fixed effects model, it dropped the variables that were time invariant, because we can't estimate those separately from the individual fixed effects. It found a return to experience of about 9.9%, although there's an experience squared term as well, so the interpretation is not quite what I just said. And then we've got the random effects model. So the random effects model is going to give us the variance of the A and the variance of the epsilon. So we have those two variances from our learning model, and it's going to report somewhat similar results for the experience and the experience squared, but then we're also able to recover the coefficients on these time invariant variables as well, because we're making the assumption that the x is independent from the AI. All right, so then we can look at the belief updating. So the first 15 rows are the first 15 time periods for the first person in our data. And whenever the wage is 999, the signal is 0. It just means no signal was received in that time period. So the first signal is 0.07, and the prior belief was 0, but the posterior belief is 0.04. So the person doesn't give complete weight to the signal because they know that there's some noise in there, but it gives close to half. And why is that close to half? Well, basically, if we go back up here, these two variance components are nearly the same. One's 11%, the other's 9%. And so given that those are equal, then we're basically going to split the difference in this signal relative to what the posterior is going to be. And then we can also have our variance belief decline by quite a bit in the presence of this signal. And then the person gets a really negative signal in the next period, so they're going to update their belief quite a bit from that because they're still not sure about what that true value actually is. And then we can just follow this process. By period 15, they've gotten 12 signals. Their variance is quite small, and their posterior is quite large because they've gotten a strong sequence of, or a long sequence of strong signals over here. And then the next person can be similar, where they start out with a 0 prior, they get a small negative signal. That's going to turn into an even smaller posterior because the variances are roughly equal. And then by the end of the panel, they're getting a long sequence of positive signals, which is going to have them infer that their true ability is positive and close to that number. So that is a little bit about how you would estimate a very simple unidimensional learning model where we've assumed away any kind of econometric selection. Obviously, if you were doing this for real, you would want to take into account any kind of endogenous participation in the signal. And so in that case, you would need to write down a more complicated model, and we'll talk about that a little bit at the end of the next video. But the next video will basically do the same thing that we just did, except for the multidimensional framework, where individuals could get multiple signals at the same time and are learning about a vector of abilities. So hopefully that will be helpful when we get there, and I hope to see you in that video.